Okay, so we wanted to understand about the Jordan curve theorem, which is about Sn, and we remove a subspace that's homomorphic to Sk for some k less than or equal to n. But it turns out to be best to start by considering something a bit different, where we just take Sn and we remove some x, where in this case x is not a sphere, but is homomorphic to a ball. Okay. So to describe what the result is there, let's just introduce some terminology. So a space X is acyclic if the homology of X is isomorphic to the homology of a point, which is the same as saying that H naught X is isomorphic to Z, and HKX is naught for k bigger than 0. And it's not hard to check. This is the same as saying, let's look at the constant map P from X to a point. So you get a constant map from X to a point, and then that gives you P lower star from the homology of X to the homology of a point, and we're basically saying that that's got to be an isomorphism. So a little tiny bit to say here. I mean, well, in degrees above 0, any map from 0 to 0 is an isomorphism. So we're not really saying anything there. In degree 0, there's a sort of slight point here that if H0 X is isomorphic to Z, then that means that X has a single path component. That single path component gets sent to the single path component of a point, and therefore this P lower star is an isomorphism. So if H0 X is abstractly isomorphic to Z, then this particular map is actually an isomorphism. Okay, so the proposition is that if X we've got some X subspace of Sn, and it's homeomorphic to the K ball, or equivalently it's homeomorphic to the cube 0, 1 to a K. It'll be more convenient actually to work with this kind of cube thing. Then the claim is that Sn, and you remove X, is acyclic. Okay. So notice, of course, that maybe said obviously contractible spaces. Contractible spaces are acyclic. Acyclic spaces very often contractible, but not always. So we're not claiming that Sn less X is contractible here, but we are just claiming that it looks in terms of homology as though it was a contractible. Okay, so we'll have some lemmas and various discussion before we really get into the proof of this proposition. Okay. But here's one kind of lemma that's kind of useful for setting the scene, as it were. So suppose we've got some two subspaces, Y and Z in Sn, and let's suppose they're closed, and I'm going to suppose that Sn less Y, Sn less Z, and Sn less Y intersects Z let's suppose these three complements are all acyclic. Then I want to claim that if I remove the union, that's also acyclic. And the proof of this is not very hard. Well, let's put U is Sn less Y, V is Sn less Z. Okay. So remember, complements turn unions into intersections and vice versa. So U, that means that U union V, that's Sn less Y intersect Z. So what we're saying is that UV and U union V are acyclic, and we need to show that U intersect V. Okay, so U intersect V is the complement of the union, right? So complements convert unions to intersections and vice versa. So we've got that these three, the UV and U union V are acyclic, and we want to prove that the intersection is acyclic. And of course, we can use the Viator-Torres theorem for this. So we've got a Viator-Torres sequence. So you've got HK of the U intersect V goes to HKU plus HKV, and then here you've got HK plus 1 of U union V. Yeah, and so for k greater than or equal to 0, this HK plus 1 of U union V, U union V, we're given that's acyclic, so that's going to be a 0. And then this one is going to be 0 when k is strictly positive. Okay, so when k is strictly positive, you've got your HK of U intersect V sandwiched between two groups that are both 0. Okay. Yes, I think I'm just going to leave the case of H0 of U intersect V as an exercise. And of course, you do that just using the bottom end of the Viator-Torres sequence. Okay, so now let's suppose that X we've got some X in Sn, which is homeomorphic to 0, 1 to the K. Yeah, so we're going to choose some F from choose a homomorphism like that. Okay. And so we want to prove that that Sn with X removed is acyclic. Okay. Okay, so suppose we've got some subinterval AB of the unit interval, and we take 0, 1 to the k minus 1 crossed with that, so then the image of that we're going to call a slice of X. Okay, so in particular we could A could be equal to B. Okay, and by the width of the slice I just mean B minus A. So if B B equals A, then the slice is homeomorphic to 0, 1 over k minus 1. So we can assume inductively that if if we remove a k minus 1 dimensional cube, then the complement of k minus 1 dimensional cube is acyclic. So we can assume that by induction. So we do need to start that induction. In other words, with the case k equals 0. So what happens if we remove a 0-dimensional cube? Well, a 0-dimensional cube is just a single point. So you take a sphere and you remove a single point, then by stereographic projection, you've just got an Rn, and Rn is contractible and therefore acyclic. Okay, so that induction can start, and yeah, so we're going to do this inductively. So we're saying that slices of width 0 have acyclic complement. Okay. Okay. So now I'm going to outline a method of proof which kind of doesn't really work, but which kind of gives you an idea of how you might start to do a different proof which does actually work. Okay. So let's call it a promising approach. So we've got very thin slices. Okay, so it seems reasonable to suppose that if slices of width 0 have acyclic complement, then slices of width just very tiny should also have acyclic complement. Okay. So we divide x into very thin slices. You know, so in the previous lemma, so we take y and z to be adjacent slices. So y intersect z is going to be a slice of width 0. If you divide your interval divide the unit interval in an obvious way into sort of a million subintervals, then each pair of subintervals intersects just in a single point. So each pair of slices of width 1/millionth, their intersection is a slice of width 0. Okay, so and then you just repeat this. You add in more and more slices. So the complement, you take any block of adjacent slices, you take their union, the complement will be acyclic. And so you build all the way up until you've taken the full block of all possible slices. That gives you the whole set X, and you see that X has adjacent complement. So that seems good, except that this first step we didn't really justify, and it seemed actually not really possible to justify it as it is. We have to sort of reorganize these ingredients in a slightly different way to get a proper proof. Okay, so then the proper proof is kind of going to be it's going to be by contradiction. We're going to assume that we've got a non-zero class in the cohomology of complement in the homology of the complement of X, and then we have to work through and derive a contradiction. So for that, we just need another lemma, or a couple more lemmas. So this one. It's the same sort of setting as the lemma we had a minute ago. We've got so y and z are both closed subsets of Sn, and yes. And we're again going to assume that the complement of y intersect z is acyclic. But we're not going to assume that the complement of y is acyclic or the complement of z. We're going to do some slightly different sort of thing. So we've got inclusions here. So remember the complement of y union z, that's the intersection of its complements, and so that has inclusions going into Sn less y, and we'll call that one I, and this one we'll call j, going into Sn less z. Okay, so we're going to suppose we've got some non-zero class here. So a non-zero class, and then kind of a little additional point for the case n equals 0. I'm going to suppose that I'm going to suppose that if you've got the constant map from Sn less y union z to a single point, and then you apply p lower star to this class u, I'm going to assume that's 0. So then the claim claim that yeah, so one or the other of these images under the I lower star or the j lower star is going to be non-zero, and the proof is, well, it's basically the same as what we said a minute ago. We've got again, we're going to put u as Sn less y, v as Sn less z. U intersect v is then Sn less y union z. U union v is the complement of the intersection. So we're assuming that U union v is acyclic. That was our assumption up here. Complement of the intersection is acyclic, in other words, the union of the complements is acyclic. and U is a non-zero element in HM of the intersection. So we've got a Myers-Torres sequence. So we're looking here at HM of U intersect V, and that goes to HMU, direct sum HMV. And remember what this map is. This consists just of the I lower star and the minus J lower star for the same I and J that we had here. And then coming in here, you've got the connecting map delta. But this group here, because U union V is acyclic, so this group here is 0. Our delta is 0, so that implies by injectivity, by exactness, that I lower star minus J lower star is injective. And that means that the pair I lower star U minus J lower star U is not the pair 0, 0, and that's all we were claiming. Okay, so what goes becomes non-zero one way or the other. Okay, then one more lemma. Okay, so okay, so we're going to suppose that U is a topological space which can be written as the union of some sequence of open sets, each one contained in the next. So, like, for example, U could be the reals, and then UN could be the interval from open interval from minus n to plus n, that sort of thing. Okay. And suppose I've got some chain W in CP of U. Yeah, so I want to claim that W is in CP of UJ for some J. So proof, well, okay, so we express our W as a linear combination with integer coefficients of these maps from delta P into U. Now delta P is compact. It's a bounded closed subset of order P plus 1, and Wi inverse of Uj is open. And delta P, well, the preimage of the whole space has got to be that. So that's the union from J is 0 to infinity of W inverse of Uj. So that means the sets W inverse Uj they form an open cover of delta P. So that means there's a finite subcut. So that means that delta P is contained in this union here. But yeah, but these UJs are all nested inside each other. Therefore, so that means that this union is just equal to the last thing in the union. It doesn't because everything's nested. So we conclude that this okay, so all of this should have been a WI, right? We've got just looking at a single WI for the time being. So Wi of delta P is contained in Wj for some j. J depends on I. But yeah, if you just take, you've only got finitely many of these W's, so you take finitely many of these J's, you take the max of them, and so now each of these Wi delta P's are in Uj, and that means that W can be regarded as a chain in Uj. So it's the compactness of the simplex, which is the key to all this. So the corollary of that suppose we've got some class A in HNU, in HN of U0, and A maps to 0 in HNU. Okay, so we're assuming we've got the same chain of U's as in the previous lab. Okay, so you've got U0 is the first set, U is the union of all our sets, and we're going to assume that you've got an inclusion of U0 in U, and so we can apply that to this class A in the nth homology of U0, and suppose we get 0. Then the claim is okay, so to prove that, well, we just choose, we've got this class in homology, we choose a representing cycle, Z in Zn of U0. But then A goes to 0 in HNU means so that means that there exists some W in Cn plus 1 of U, dW equals Z. Okay, that's what it means to say that this homology class is 0. It means that Z must be a boundary, must be an image of D. But the lemma tells us that this W is in Cn plus 1 Uj for some J. So that means that we already see that Z is a boundary in uj. We don't need to go all the way up to u, so that means that the this class goes to 0 in the homology of uj. Okay. So now we're ready to give the proof of the generalized Jordan curve theorem, but I'll put that in the next video.